How's it going, everybody? So today we're going to be talking about how to solve exponential functions and logarithmic functions, and we're going to be trying to make sure we solve for that x value. Now, when we utilize all the things that we've learned, we have to incorporate this one new idea, okay? This is called the property of equality for exponential equations. Now, what it's trying to say is that if I have this 3 to the x is equal to, say, like 3 to the 5. Notice how the bases are the same, okay? What they want you to understand is that if the bases are the same, then you can actually simplify the bases and you can immediately put what's in the exponent equal to each other. So I can now go x is equal to 5. Now, that's essentially the rule. So say I had something like this. 7 to the x minus 1 is equal to 7 to the 4th power. Then, because the bases are the same, I can put the exponents equal to each other, and I have x minus 1 is equal to 4. Now, I then solve, well, add 1 to both sides, and you got x is equal to 5. Okay? So, that's just an idea of how we're going to incorporate this idea, and I'll show you how logarithms work in a little bit, but for now let's focus on the exponentials, okay? Now let's actually get into a nice real problem. So I have 100, okay, to the x power is equal to 1 over 10 to the x minus 3 power. Now, looking at this right here, because we're working with exponentials and we're trying to utilize that identity we just learned, we want to try to get the bases on either side to be the same. Well, for starters, let's go ahead and make sure we can get this fraction to be a whole number. So let's move the 10 to the numerator by raising it to the -1 power, okay? Because if you do that, you just got to raise it to the -1. Now, looking at the left-hand side and the right-hand side, we see that there's a 100 and there's a 10. Well, we know that 100 is actually 10 squared. And so remember, we're going to have to be comfortable looking at numbers in a different light, being able to see, like, 49 is equal to like 7 squared. Okay, so we're going to have to remember our multiples, remember our, our squareds. Okay, and so looking at this, we now have 10 squared to the x power is equal to 10 to the -1 to the x minus 3. Now, utilizing our properties of exponents, okay, the power property, we can go ahead and distribute this x into here and distribute this x minus 3 into here and multiply them. So this side will be 10 to the 2x because 2 times x is 2x. And then here, I've got 10 to the -1 times x minus 3. Now, I'm drawing a lot of steps to show everything, but the idea is this then gets distributed in. And I have 10 to the 2x is equal to 10 to the -x plus 3. Now, we have bases being the same. They will simplify out, and I have 2x is equal to -x plus 3. Now, looking at this right here, we combine like terms. We're going to add this x over to the left-hand side, and that's going to give me 3x is equal to 3. Now, that's very convenient because when you divide by 3 on both sides, what you're going to get is x is equal to 1, okay? Now, the idea is that you should be able to plug this back into the original equation, and of course, they should be equal to each other. And have the same number on both sides, okay? So now let's do another one. Alrighty, guys, let's take a look at something like this, okay? Say I were to give you, let's do 2 to the x is equal to 7, okay? Now, I'm showing you this because I want to dive deeper into this property of equality, because I know that we basically said that if I have something like 2 to the x is equal to like 2 to the x minus 4, you could just simply put the exponents equal to each other. But you have to understand that that's like a perfect scenario. That's if, someone decided to make things work out nicely for you. And sometimes it does and it can happen. But in the real world, a lot of the time, it's not always that pretty. Sometimes you're given these types of exponents to solve for. And I want to show you exactly the mathematics of why those properties exist, okay? So in truth, what we're actually trying to do to get that x out from the exponent, we're actually doing this. We're actually going ahead and doing log base 2 on both sides, okay? And let me actually write this on either side. So I'd have log base 2 of 2 to the x, but what I do to one side, I do to the other, and I'd have this. Now remember, the log base 2 will simplify with the 2 and leave you with x is equal to log base 2 of 7. Okay, and of course that doesn't simplify, and so you would type log base 2 of 7 in your calculator, and you should get roughly x is equal to like 2.807. But I'm showing you this because if you go back to the one we originally did and kind of jumping back into this spot, you don't have to write this, but just kind of showing you. I could have done the same thing. I could have done log base 10 of 10 to the 2x is equal to log base 10 of 10 to the negative x plus 3. But that's why the identity, that's why the property exists, because if you look at it, these will simplify on both sides, so 2x is equal to negative x plus 3. So that's why that property says that if you have the same base for an exponential function, their exponents can equal each other. But I didn't want it to seem like, oh, it's just magic and that's why it happens. No, it's because they're actually applying a log base 10 or whatever the number needs to be to each side to actually simplify it, leaving you only with the exponential function, or not with the exponential, but with the exponent left, okay? So that's kind of the idea, okay? So let's do one more. Here's a real life application. We're going to be talking about Newton's law of cooling. Okay, so the equation is displayed up there for everyone to see. It says that T sub O is the initial temperature, and then the temperature T after T minutes can be modeled by the overall equation. Okay, now looking at this, it says TR is the surrounding temperature and R is the cooling rate of the substance. Okay, so the first thing we're going to need to do is we're going to need to kind of identify all of our factors here. So it says you are cooking a lika. I'm not sure how to say that, but it's an Ethiopian stew. And when you take it off the stove, its temperature is 212 degrees Fahrenheit. The room temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is 0.046. How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? Now, if anybody can actually look up how to say this word right here, I would actually appreciate it. So one day I can maybe do this example again and actually say it right. But as far as I know, it's going to be called Alika for right now. Alrighty, so it says we have some different things we need to put into our overall equation here. So it says we have our temperature at 212 degrees Fahrenheit. So that's going to be important, right? That's the outside temperature. That's the initial temperature. So we've got our T sub O is equal to 212 degrees Fahrenheit. And then the temperature of the room, right? So that's going to be our T sub R, right? Because that's the surrounding temperature. So T sub R is equal to are 70 degrees Fahrenheit. And the cooling rate of the stew is that 0.046, right? So R is and I'll put the 0 there too, 0.046, okay? How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? So we have it at T equals 100 for when I guess we're trying to give it to people, like maybe for them to eat or actually be served with. So we got to go ahead and solve for our initial t, right? Because it wants to know the time that it will take. So we've got 100 is equal to 212 degrees Fahrenheit minus the 70, because that's the surrounding temperature, it times e to the negative, and it'll be 0.046 t plus, and it looks like we're going to use t sub r again, so then we have 70. Alrighty, now let's keep going. So we're going to need to go ahead and do some calculations, okay? So if you have your handy dandy calculator, go ahead and break it on out because you're going to need it. And let me get my calculator out as well. So I've got the 212 minus the 70. Let's do that. That gives me 142 e to the negative 0.046 t plus my 70, okay? I'm now going to go ahead, let's subtract 70 to either side. So I have 100 minus the 70, that's 30, right? So that's going to give me 30 is equal to 142 e negative 0.046 t. Okay, and let me kind of shrink things a little bit so I have some more room here. Now, what I need to go ahead and do is I need to divide the 142 to the left-hand side so that way I can get e by itself, okay? So 30 divided by 142, that's going to give me a pretty small number. It's going to give me 0.2112676, and I'm just writing a lot of it so that way I can have a good quality answer. And then I have e to the negative 0.046 t, okay? Now, looking at this right here, okay, this kind of falls into that category of we don't have bases are the same. Technically, on the left-hand side, you have a base of 0.211267661, right? And on the right-hand side, you have a base of e, okay? But that doesn't mean we still cannot go ahead and apply a log to go ahead and simplify both sides. So, believe it or not, the log that gets rid of a base of e is a ln, okay? So ln gets rid of that. So we have ln of 0.211267661. And then the ln of e to the negative 0.046 t, okay? So these will simplify out, right? And we can actually do the ln of that really long number on the left-hand side. And that gives me, it looks like a negative number. It gives me a negative 1.5546, okay? And that's equal to our negative 0.046 t because we simplified its base out. Now it looks like all we have to do is divide out the negative value on the right-hand side. So we divide by I have to go back and write it. So I got 1.5546 divided by 0.046, and that gives me a not a temperature, but a time of 33.8. So T is going to equal 33.8, okay, for this problem. Now, what is it describing? Well, it goes back into the problem and says how long, and its T is in minutes, right? So this is actually, and we should probably just round, the amount of time it will take is probably 34 minutes. Make sure you put units so that way you don't think it takes 34 hours, because that would not be something fun to eat. Alrighty. So hopefully that gives you kind of a better understanding of how we address these types of exponentials. And just to reiterate kind of what we learned is that if you have something like a 4 to the x is equal to 4 to the 7, the idea is that a log base 4 is applied on either side to get rid of it. And if you encounter something that is, for instance, you have a 2 to the x is equal to a 7. You can still apply a log base 2 to simplify, but you just have to do log base 2 to both sides. Okay, and so then you'd have x is equal to the log base 2 of 7. Okay, so just be aware of that. And then last but not least, understand that if you had like an e to the x is equal e to the 7, the ln is what simplifies out e's. Okay, those would go away, and then you'd have x is equal to 7. All right, so let me clean this all up, and let's keep moving on, and let's talk about logarithms. Alrighty, so with logarithms, the properties are very much the same, but it's just the reverse order, really. Because if I make the claim that the log base 2 of x is equal to the log base 2 of 7, then consequently I can say that x is equal to 7. But that has a lot to do with the idea that if I go back to this, then what I'm doing to simplify these logs is I'm raising them to the power of 2 on either side. Now that is going to actually simplify, and once again leaving you with this. So you can either view it the mathematical property where you write the 2 and simplify, or you can just understand that if you have similar bases equal to each other, what's inside the logarithm is equal to the other side as well. So let's actually do some examples. So let me erase this. So let's try this one on for size. So say I have the ln of 4x minus 7 is equal to the ln of x plus 5. Well, we should feel confident knowing the property that if I have two logs that are the same, then what's inside the logarithm is equal to what's inside the other, right? But if you want to do it more mathematically, you would say I'm going to raise this to the power of e on either side, because remember, ln and e, they have a special relationship. They are the opposites of each other, okay? They simplify. Now, this is going to go away, and you're going to be left with 4x minus 7 is equal to x plus 5. Now, with that being said, this is now really easy. This is chump change compared to what we've been doing, because we're just, combining like terms, right? So we're going to add 7. So I've got 4x is equal to x plus, and then what, 12? Subtract x. So I've got 3x is equal to 12. Divide by 3, x is equal to 4. Easy. Easy. Too easy. Now, let's try another one with a little bit more rigor, okay? All right, let's try this one on for size. So now looking at this one, you'll notice we don't have the same log on either side, but do not let that freak you out. We can handle this, right? We just have to raise it to the power of 2 on either side. Now this will simplify, leaving me with 5x minus 17 is equal to, now what is 2 to the third power? That's all we got to figure out. Well, 2 to the third power, if I'm not mistaken, is 8, right? So you've got 5x minus 17 is equal to 8. Now it's, once again, chump change, right? We're just going to go ahead, combine like terms. Let's add 17 to both sides. Nothing to it. 17 plus the 8, that's going to give us what, 25? So 5x is equal to 25. How convenient. 5 couldn't go any nicer into any other number, right? 25 divided by 5 is, of course, 5. So there you have it, okay? There you have it, folks. So let's go ahead, though. Let's keep trying these. Let me try doing this example here. Let's try this one. All right, let's try this one on for size. So you have a log, two logs on the same side, right? And then, of course, you have this random 2. You can actually apply the product property of logarithms to the left-hand side, and that would give you log of 2x times x minus 5, okay? So we're now applying things we learned from the last set of notes. Now let's go ahead and distribute this inside. So we have the log of 2x squared minus 10x, okay, is equal to 2. Now remember, if you're dealing with just a log and it doesn't have a base, that's because we consider that the common logarithm, and it's actually should be written like this, but because we as mathematicians and as people, we've become very lazy, We just leave off the 10. But we can still raise this to the power of 10 on either side, and it will simplify. So you have 2x squared minus 10x is equal to 10 squared. Well, that's going to give you 100. Now, if you can't see what's happening yet, you're going to be in for a treat. But if you do, hopefully you're excited, because we're going to move that 100 to the left-hand side, and you're going to have 2x squared minus 10x minus 100 is equal to 0. And looky there, it's a quadratic equation. Just when you thought quadratics were gone, they're back. And so now we can go ahead and do the AC method, or use the quadratic formula to solve for x. Or you could, maybe simplify first. That would actually be a better idea. Let's go ahead and do that. Simplifying it first would give you some nicer numbers and make it probably a little bit more easy to stomach. And we have something like this now, okay? Now, in my opinion, it is a lot easier to factor. I think it's better than the quadratic formula, because if you look at negative 50, the numbers that will add up to negative 5 are going to be negative 10 and positive 5. That would work out just fine. And so you, of course, would have your x squared minus your 10x plus your 5x minus 50 is equal to 0, okay? And then, of course, split down the middle, x, and then x minus 10. And, of course, x minus 10 will pop up over here. And then you have a 5 on the outside. So you'd have x minus 10, x plus 5 equals 0. Solving for both of these values on either side, you'd have x is equal to 10, and then you have x is equal to negative 5. Okay? Are you done? You are not done, because, guys, you cannot assume that these answers are perfect answers. One of them could be extraneous. And believe it or not, I actually do know this just because I'm kind of looking at it, and I believe it's going to be the negative 5 is extraneous, okay? So test that for me. See if the negative 5 is extraneous, because I did a little math in my head and then I guess just jot it over to the side. But negative 5 should be extraneous and should not be an answer. The only one should still be your positive 10. And the reason for that is because if you start putting negative numbers into logs, it starts to not like that, okay? And so that's why. And because if you remember, the graph of a logarithm, it doesn't pass the asymptote, which is the y-axis, and it only exists on the right-hand side, only on the positive values for x. So if you start plugging in negative values for x for a logarithm, it's not going to work because the graph itself only exists on the right-hand side. So any negative value of x should be undefined, okay? That's where my thought process went, okay? Alrighty, so let's go ahead, maybe do one more, and then we'll call it good. Alrighty, last one. So we have our log base 4 of x plus 12, and then we have our plus log base 4 of x is equal to 3, okay? Now, looking at this right here, we can go ahead and apply the property where we, if they're adding, they can now be multiplying underneath one logarithm. So I've got x and then x plus 12, and then is equal to 3. Now, looking at this right here, I'm going to go ahead and distribute this in. So I've got log base 4 of x squared plus 12x is equal to 3. I'm going to raise it to the 4th power on either side to get rid of the logarithm. Now 4 to the 3rd power, that's going to be, I believe, 64. Oh, let me just double check, because 16 times 4. Yep, 64. So I've got x squared plus 12x is equal to 64. I'm going to bring it on over. So I've got x squared plus 12x minus 64 is equal to 0. Now I got to think about negative 64, and I got to consider, what's a, multiple that will give me that positive 12 that I'm looking for. And it's actually going to be your 16 times 4, and I believe it should be 16 times your negative 4. So you're going to have your x squared plus 16x minus 4x minus 64 is equal to 0. Split it down the middle, and you've got x and x plus 16. Yeah, and then you'll have an x plus 16 over here, and you're going to go ahead and bring out the negative 4. Now, as we keep going, you would end up with x minus 4, and then x plus 16 is equal to 0. And then x will equal 4, and then x will equal negative 16. Now, going back to that idea, I believe this x equals negative 16 is extraneous, because if you start putting negatives into those logarithms, they become undefined. And so you can only put positives in there, and you can put negatives in there as long as it doesn't make the inside of the logarithm negative. Because if you start doing log base 4 of negative 16 plus 12, then this plus 12 doesn't get it to be positive inside. Now, had you had like log base 4 of like negative 16 plus 17, then yes, x equals negative 16 would have been totally sufficient, but just understand that currently right now it's making the inside of that logarithm negative, okay? So that should be it for this video. Let me know if there's anything else I can help you with, guys. Keep me up to date. Hope you guys are doing good. Talk to you later. Bye.